Yeah, now the slides are changing.
Okay, no? It's changing, right?
So one more thing, you switched, your camera is on, right? But we can't see you.
Yes, yes. I have just closed
Ah,
the
okay,
shutter.
then. That's it.
Mhm. Did you all switch my screen share or just hello? Hello?
We are extremely sorry for the delay, guys. We will start in few minutes. Good evening, everyone, and a very warm welcome to all of you joining us today. On behalf of the organizing committee, I'm happy to welcome you to this online technical session on IoT problem solving approach conducted as part of the SLIoT Challenge 2026. This is Sri Lanka's premier annual Internet of Things Innovation Challenge that brings together school students, university undergraduates, and open innovators to develop real world solutions using IoT. It is organized by the Department of Computer Science and Engineering, University of Moratuwa, in collaboration with SLT Mobitel and Institution of Engineers, Sri Lanka. As part of the proposal submission stage, we are conducting 2 online technical sessions in collaboration with our industry partner, Zone 24/7. Today's session is the first session of this Zone 24/7 series, and it focuses on something very important: how to approach and think through problems when designing IoT solutions. Now, moving on to our speaker for today. It's my pleasure to introduce Mr. Dewmith Ranasinghe, electronics engineer at Zone 24/7, who will be conducting this session on IoT problem-solving approach. In this session, he'll be sharing practical insights on structural thinking, identifying the right problem, and aligning your ideas technically, which will be extremely useful for strengthening your proposals. I encourage you to note down your questions as the session progresses. Without taking any more time, let me hand over the session to Mr. Dewmith Ranasinghe. Sir, the virtual stage is yours.
Thank you, Madhumai. So am I audible to everyone?
Yes, sir, you're audible.
Is my slide shared?
Yeah.
Okay. All right. Good evening, everyone. I'm Dewmith Ranasinghe, electronics engineer working at Zone 24/7. So today you all have all come for an awareness session in IoT about approach to solve a problem using IoT. So today in this presentation, during this session, don't expect for me to teach you all about coding, sensors or cloud platforms, or how to push data, which MCU to use. I won't be using this. I won't be teaching about this. I will give you guys good understanding about first identifying the problem and from there onwards designing a successful IoT solution. Because now this IoT competition, you guys are not undergraduates anymore. You guys have to work and think like engineers. Because in the industry, a client won't come and ask us to use a ESP32 or MQTT protocol. They will be like, our machine is failing, fix it. So then we will have to identify the problem statement, and according to that, we will have to deliver our solution. And also, I would like to say, since there's a limited time constraint, I would encourage the audience to drop in your questions in the Q&A box. So at the end of the session, it will be easy for me to answer each and every one. So let's move on to the agenda for today. First, we'll talk about how to identify an IoT problem, what an IoT problem is. Why do you need IoT to solve that problem? And also, I would teach you step by step how to design a perfect IoT solution. And also, we will talk about a case study, a real life case study that we actually worked here in our company. And also, finally, I will explain you about the learning outcomes and key takeaways of this session. So today, my objective is to give you a good understanding about breaking a problem into small parts so that you can use each of these parts to build a solution. And also systematic thinking. And there are common mistakes that we all do when designing an IoT product. Even when I was an undergraduate, I did the same mistakes. So normally we will start straight away from an ESP32. Straight away we'll go start from a things board server and we'll start building that. That is not how to design an IoT. So let's see. So how we do it, and at the end of this session, you will have a good idea about it. So first of all, what is an IoT problem? And I would like to take this session very interactively, so please feel free to drop in your answers. What do you think an IoT problem is? Anybody? The moment we hear the word IoT, it doesn't mean just a bunch of sensors together with internet. That is not IoT. And why do we need IoT to solve a problem? So let me explain. Say a client comes to you and says the machines they are using the factory are overheating. Or a CEO would come to you and will be like, a CEO would come to you and will be like, once our after office hours, still our energy, our electricity bill is spiking up. And a farmer would come to you and be like, my crops are not working. So these are problems. These are not yet IoT problems, but these are actual problems. But IoT problem is something that is not working inefficiently. And also, it should be able, that problem should have quantities that we can measure. And if we measure quantities, we get data. And also, we should be able to analyze that data. Still, it's not enough. And there's the analyzed data, we should be able to act upon and get the necessary outcome. So that is what an IoT problem is. So let me tell you why IoT problems are different from software issues. So in a software issue, in a software problem, you have perfect internet. Most cases. And if there's a software failure, if there's a bug, you can do a firmware update. But in an IoT problem, if the device is not working in the remote area, if the device stops working, or if there is a power failure, or if there is a connection failure, the whole system would come down. So it is that is why it is very hard to design a perfect IoT solution in comparatively with just a software solution. And that is exactly why we need an IoT solution. So today's main topic is how to describe or how to set up a proper problem, how to create a proper problem statement. So most of us, even during the uni time, what are we going to do? What normally we go in front of our lecturers and we be like, just building a weather station. We're going to collect the data. We're going to monitor the temperature. We're building this dashboard. So is that the problem? That is not the problem. That is just one part of one component that we're explaining. But what we have to say is, why do we need to monitor the temperature? So we have to be like, so we are going to make this system efficient. We are going to make sure that this machine downtime is, we are going to reduce it by 20%. Or we are going to make sure these crops are properly grown throughout the year. So that is the problem definition. That is how we properly build the problem, the objective, and not what we're going to do. Because without a clear objective, without a clear purpose, we cannot build an IoT solution. So that is what I want to emphasize a lot, because one thing we always do is we start from the end. We start buying hardware, we start building dashboards, and we started collecting data, but we at the end of the project we don't know what the outcome is or what it solved eventually. So that is the mistakes I want you guys, like I want to explain properly, so that you all won't make that same mistake when you are developing your IoT product. So let's see how we're going to do that. So I'm going to break it down to 5 steps. First steps is defining the real problem. That's number 1. And second, we are going to understand the constraints for this said problem. Say we are going to give a solution. There are always constraints, limitations, what we can do and what we cannot do. And once we understand the constraints, we are going to move on to designing the architecture. What will be the devices we're going to, that is where normally we start, but that is the third step. Then only we realize, okay, now we have the constraints, we have a proper objective. Okay, now what's the minimum, what is the device, what are the devices we're going to use for this product, what is the connection type we're going to use for this product, what are the visualization methods that we're going to use to depict this data. And after that, we're going to come to handling the data. So just because we collect a temperature reading, a humidity reading, or whatever, a small raw data, that is still half of the project. Because as long as you don't give meaningful outcome, a meaningful visualization to those data, and those data, still, just collecting the data itself is not enough. So once you have properly analyzed, filtered, put these data through various processes, and finally bringing to a larger picture in visualization, then there we can give a meaningful outcome from your IoT product. And finally, something that we don't always think is securing, because IoT product is a product that is not in a single place. It is spread across a large area. So there are different devices on one side, and there's a different processing on another side. So, and we are always working with data, and sometimes it can be actual sensitive data. So we have to go another extra lane to make sure our system is secure, so that it cannot be tampered by a third party. So let's go through each one of these steps throughout the session and see how to build a productive IoT system. Step number 1, identify the real problem. Like I mentioned before, first the problem. That's the important step. So when we are going to identify the problem, how we are going to do it? So now all of you all have submitted your products, product applications, right? So definitely you have. So how many of you all have identified the problem correctly? So if I ask one of your teams, what is the problem you're solving? Question number one. Second question, who did you talk to regarding this problem? Actually, who is the human component that is affected by this problem? Whether it's a farmer or a machine worker, or a doctor or a CEO, whoever. Who is the who is the human component that is affected by this said problem? That's the question number two. The question number three is, currently, right now, how is it solved? I mean, you are giving a solution to an already existing setup. So somehow right now they are trying to manage it, but they are failing, but somewhat they are trying to manage it right now. So what is the existing system that they are using to manage it? And the final question is, if you keep on continuing without an IoT solution, what will happen? What is the cost? How bad it will affect the business or the human component? So this, if each and every one of y'all answer these questions, you are going to get a sound understanding what the problem is. So that is step number one. So I want all of y'all to note it down, short way, because when we come to the latter part of the session, we'll be doing a case study. So in a case study, I'll be the client and you are going to be the engineers. So I'll be explaining you all a real world project. So I want you all to go through each one of these steps and design the IoT system. Okay. So now after properly identifying the problem, now you can give this is the place where you change from non-technical language to technical language. So now they have answered all your questions. Okay, now we end that's so all those 4 questions I asked before, now they have answered. So for example, now let's say a farmer, you ask the farmer what's happening, they say these crops are dying and you don't even he doesn't know what's happening. So he just wants to manage he wants to make sure that his crops are growing throughout the year. So the farm is affected, the person who so that's the human factor. And so because of that his business is affected, so that is the cost. So now you in this stage, now you're going to slowly transition those questions into technical language. So you'll be asking, okay, what should I sense in order to make sure that these crops are not dying? So you can ask these questions yourself. And how often should I sense this said data? And also how what decision depends on this data? That's an important thing. So say now you are measuring the soil humidity, like the soil moisture. So now you measure the soil moisture and you're going to then make sure how often you're going to measure the soil moisture. Let's say twice a day or once every 2 hours, you're going to make the period. And just because you measure the soil moisture, is it enough for you? Can you decide why this crop is exactly dying from just soil moisture? That's the thing. So because it doesn't matter, you all plugging a number of sensors and measuring all this data if nobody is going to use it. Because most of the things that most of the mistakes even I have done, I have seen in a university period is that we use a bunch of sensors to read a lot of data. But in the end, we are not going to use all of them. We're going to use a couple of them because in this stage, we think collecting a large amount of data and having thousands of rows and columns of data is a superb thing for an IoT project. That is not. As an engineer, the first thing that you all should do is the first principle of engineering is if you can do something, do it in the most simplest way. Please do not overcomplicate it. Do it in the most simplest way. So first, once now you all know what the problem is, so you all research about the problem and see what exactly do I need, what's the data exactly you need to detect whether this plant or died or not, or whether this machine is overheating or not, or whether this room is using a lot of energy, like a lot of electricity power or not. What are the exact amount of data that you should read? So that is what you should decide. So once you have a very sound idea of what data is used, I mean, it can fail. I mean, once maybe during the middle of the project, you all understand that this data is not wrong. That is that is engineering practice. But that doesn't mean in the beginning of itself you all bring all the sensors in the world and do it. No. First, what is essential? So after asking all these questions and after making sure that you have understood the problem clearly, and once you build this solution that the human factor, the farmer, doctor, CEO, whoever is gonna get a good benefit, then you all create a problem statement, because now you have a clear goal, you have an actual impact once you develop this project, and there are measurable quantities. Okay, so I've given an example. Reducing energy wastage in office buildings using the real power monitoring. I mean, I know you will have by this time in all these proposals there must be lovely problem statements. I'm pretty sure. But writing the problem statement is not the thing. Understanding what the problem is the most vital thing. I'm emphasizing so much on this because it's if you really think about it, it's the layer. It's a very boring part to actually talk about and have this questionnaires and ask people what the problem. But the moment you actually go through these steps, it will be very beneficial in the latter stages of the product. Because I'm telling you by experience of the mistakes that we have done as an undergraduate and even in the industry practices, the practices that I've learned. So once you have a solid problem statement and once you have identified all the constraints of the problem, you have actually completed 50% of your product. I can assure you that. So our step now 1 is done. You all can drop in questions if you all have, if anything is unclear. Let's move on to the second part. Okay, now we have a solid problem. Now we're going to understand the constraints. So what do you mean by constraints? I mean, at a glance, normally at once we understand constraints as limitations. Yes, there are limitations, but these limitations are actually design inputs. So constraints, we can mainly categorize into technical constraints and environmental constraints. So as an undergraduate, when you are developing your IoT product, most of the development will be done in a very secure place, inside a lab, inside a classroom, and you'll be, or maybe just outside your university. That's the environment we use. But if you go back to the problem statement, what you have to think is your product actually work in that environment? So if we talk about the main constraints is first the budget. So this is one thing we never have a track on, because for a successful product to come to the market, any product, IoT software or embedded, any product in the world to come into the market, there has to be a good cost management. Because at the end of the day, no matter how good our product is, if it's too expensive, nobody's gonna buy it. If say the product is 1,000 rupees, if we can't deliver 1,000 rupees worth of function from our product, nobody's gonna buy it. So that's a failure. So from these days onwards, think like an engineer. Always consider your product. Always consider the cost when designing your product. And also like I mentioned, the environment, the actual environment that is going to be used. Power. Power is a very vital thing when it comes to an IoT product, because not all the edge devices are placed in a very secure, uh, full-time power available area. Maybe edge devices will be deployed in very rural forestry areas. So power is a constraint that which has to be always thought of, and definitely the connectivity and also the scale. So this scaling is also one point that we always miss. Normally, power and connectivity in this level, we always think about power and connectivity. That's one thing we think about. But if you want to have a successful product in this competition, make sure your product is cost effective. Make sure that it is gonna work, not theoretically, practically. It is gonna work in this set environment where it's gonna be deployed. And also the final point, scaling. Scaling means your product should be able to easily scale to a larger quantity, or the other way around, to a minimum quantity. So if you have first deployed 5 nodes, within a shorter period of time, you should be able to increase it to 500 nodes, and the whole network shouldn't crash down. The network should be able to properly coordinate all this increasing of units. So that is what scaling means. This is a very, very important design constraint when it comes to IoT products, and especially now you are going to submit into a competition. So make sure that you all have proper justification for all these constraints when you are explaining your final solution. So environmental constraints, like I said, indoor versus out, temperature, humidity, dust, vibration, and say your edge device will be deployed in an factory environment. So the factory environment means there are so many interferences than in an outdoor environment inside a factory environment, because factory environment, heavy machinery is always on. So that means there is a ton of electromagnetic interference from this machinery. And also there's constant vibration. And there's definitely dust in some factories. There are no dust in some factories. It depends on the product. But these are very important, because you have to always think about your final product. Just because you get an IP64, IP68 rated enclosure and just make sure, okay, my enclosure is IP68 or nothing is going to happen. No. IP60 is not going to protect you in an industrial environment. So because that has a different type of parameters running inside. Maybe IP60 would help your product in an outdoor environment, but not in an industrial environment. And also distance between nodes. The connection, the node distance should be too close, because then it will counter interference. But it shouldn't be too farther apart either, because then there's a possibility to miss some data. And also one important thing is, this is also a very important point that we miss when in a university level, that is accessibility for maintenance. Say you have made the perfect solution, perfect product, you have deployed it, it's working perfectly. But does it mean that it's going to work perfectly forever? No. It's going to fail at some point. Failing is not an issue, but you should have a proper plan for maintenance. And say you also have a plan for maintenance, but if you can access the end device, end node, whenever you want, that is also a product failure. Say the power went out, you have to replace the battery. But if the device is inside inside that heavy machine, as like you have put the device as inside as possible in all these heavy machinery, like in a way that you cannot access without stopping the machine, that is a complete design flow. So there is also one thing that you have to note down: maintenance and accessibility for maintenance. So those are few environmental constraints. I am telling each one of these points, so you all can note it down, or I'll be sharing slides, and you have to apply it to your own project and see whether you all have thought about these facts when submitting your proposal, when designing your IoT product. So that is what is important. Technical constraints. So the first thing about technical constraint is this battery or main. So definitely if it's in a very outdoor rural area, you will have to go with a portable device, which is battery powered. So that is a that is a limitation that you have to work around, which is the power, because your battery should last as long as it can while powering the units with the maximum current. So you are when designing the components, you all have to trade off between power and performance and also cost. I mean, there are really, really good batteries, and that is also at the same time very expensive. Say you're gonna make 1,000 nodes. So in a production time, when you are making 1,000 nodes, so that is not effective, getting a very expensive battery. So there are trade-offs that you have to make. And if it's possible to get main power, you all should go with it. And a successful design will have both. I mean, we'll be using main power or renewable power energy source like solar or anything. And if it fails, it can change over to a battery or a portable power. And also the latency requirements. So based on your product, you all have to decide whether how fast you need to send these data. Say you are sending weather data. Weather is not going to change every 5 minutes. So you all can send the data periodically. So there is it's fine if you all miss some data or if the data is slow. But say you are actually sensing a critical point like whether for a fire alarm or energy monitoring, whether the unit is going to consume more, whether it's going to go overloading, or whether it's going to go for a high pressure, or whether it's going to, or especially other types of alarms. So that is a critical data. So that data has to be sent in a higher frequency. The latency has to be minimum. So that constraint you have to think about. You have to design in a way that you have to decide which latency requirement you're going to go to. It is a very low latency or which is a very high latency if it's not very important data. And also the other thing is data volume. Data volume means we should come up with a way to try to send data to the main coordinator in the minimum size possible. So that is a very good design requirement. I mean, you can also get creative. You can come up with your own way to break down the data and make it a single integer, or maybe like a single string, or you'll come up with a concession and send it. Because as long as you bring the data down, say now, for example, say you are sending the temperature and humidity. So you all don't need to send the decimal point all the time. You can come up with a convention that first 3 bytes will be the integer part, this last 3 bytes will be the decimal part, or everything will be in the same string. So when you're decoding it, you will be using the same convention. So you will have to try to make your data packet small as possible, the data volume small as possible. And if you're sending images, try to not send images. Try your best to detect pulses, small changes, small signals. And if your product if your product isn't enough, like if your product is a more high-end product, and if you really, really need to send images, say you're using AI model in the cloud, if you really need to send images, then try your best to optimize your image. Try to make it a very, very small, like a smaller quantity, so that you can send it easy. So that is a very important technical constraint that you have to think about. And also security. Security, I will talk about in detail in later stage. And this is, of course, an additional thing, that is regulatory requirement. Say you're actually building a product for a specific country, or you are building a product for a specific industry, say a medical industry. So products in a medical industry has to go through some regulations, so that those regulations, that product should pass those regulations when it is being produced for a medical industry. So those are additional things that you have to consider when developing an IoT product. So now we are come to step 3. So first, we properly define the problem. Now we know what the problem is. We have spoken with everyone. Okay, now after defining the problem, we understood the constraints. We went through each constraint, and we understood that our device will have these limitations. So we can design it in a way that it will support it. So now we have understood the constraints as well. Third, we're going to come to our design. Now we're going to design the architecture. So IoT solution, IoT product is made of several different layers. So first, we have the device layer. And the device layer is the first layer, which is the edge node. We normally use the word edge node. And from the edge node, we'll be sending data using a gateway, some sort of a connection way, to a coordinator or a cloud platform. And using that cloud platform, we can do statistical analysis. We can run machine learning models, and we can make those data meaningful. And once we have meaningful information, you can use those information for users, for predictions, or for other physical operations. So each layer is very important. And if one of these layers fails, that means your product is failed. Because IoT product cannot function without just because one layer fails doesn't mean the IoT product is successful. It's complete. So it's important that when you design, you have to have contingencies in each and every layer, because you have to design a product thinking that it's going to fail. So in that mindset, if you always design that whatever you do can fail, you are going to come up with plan A, B, so that if this fails, it will fail safe in a way that it will be transferred to another area. So that is a good design requirement when designing. So once we design each and every layer, then we take decisions one by one. Okay, first we talk about the edge node, the end layer. When it comes to the device, the edge node, I mean, this is, I think, the most interesting part of designing an edge node. But the question is, do we need to design an edge node? Like, do we need to design the PCB, the power, everything all by ourselves? Do we need to do that? Because the wheel is already invented, and using the wheel, humans build cars and bikes and everything on top of that. There's no need to invent the wheel again. So that is one thing that you all need to keep in mind. If there are already highly developed, cost-effective, efficient components in the market, use them for your edge nodes, because there are a number of products, industry-grade products in the market that you can use as edge nodes directly. You don't always need to develop a PCB, develop a microcontroller, get a microcontroller, use a ESP32, Raspberry. That is a traditional way of doing it. That is what we always do. Maybe for initial testing, you can use it. But try, because since you are making a product for the market, and since this is a competition, you have to think about the future. You have to think about the cost. And you have to think about the time of hours you spend designing an edge node, and you have so much to do in the rest of your product. So if you can buy off-the-shelf components already, efficient components, which actually works, with your edge node, do it, because that is a good design decision. And also, when it comes to sensors, sensing the data is another topic, because there are, for every sensor in the world, there is a cheap sensor. There's a Chinese knockoff where you can get for a very cheap price, which will give data which has the least amount of accuracy. And also, for the same parameter, you will have a very expensive industrial grade sensor, and there are many more in between. And so when you're choosing a sensor, you have to think about first the performance, second the power. That is very important. How much power does this consume? And the third is the cost. Even though I said it in 1, 2, 3, these are actually in the same level. So you have to make trade-offs when you're choosing a sensor. So if you choose a highly efficient sensor, then the cost will also be high. So you have to make sure that you make trade-offs between each of the parameters to choose the best sensor for your product. Because sometimes we choose a very expensive industrial sensor, but the data that we are sensing is not that important. So that means it's a design failure. If you have a very critical data, and if that data becomes inaccurate and the whole system will go wrong, okay, yes, you can use an expensive, good sensor. But if your data is not that critical, it's just one part to make a decision, then you can go for a mid-level sensor. And also the sampling rate. Like I mentioned before, you don't need to always read the data and send it. You have to send it when it's needed only. I will talk more about the sampling rate the next 2 slides. And also power. Power is very important, because designing a power-friendly end node is actually I'll say it's a part of a complex process, because without power, nothing's gonna work. So you have to give a good attention when you are choosing a power source, and also you should have a contingency if that power fails, because your design, your IoT product should run without any failure. It should try to run without any failure. And also that power source should be available in the actual environment that you will be deploying your end node. So there are a number of things for you all to think about when choosing a proper power source and designing the proper power circuitry. So that is important. And also local processing. So that is actually when you read data and things like that, sometimes, most times, the data is filled with noise. So you should do some local processing. You should do some filtrations for your data to remove all the additional noise from your data. I'll talk more about it in the data segment. So those are little things. So mainly your main processor. So if we divide your end node into input, processing, and output. So input is a sensor. You know what to do: cost, performance, and accuracy. Processor, whether it's a microcontroller, or whether it's a SBC, or whether it's an off-the-shelf component. And the output is how you can transfer that data, which is a wired or a wireless connection, and the sampling rate. So these are the elements that you have to think about when selecting devices. And the other interesting part is the connectivity. So, I mean, there are popular connection protocols in the world: Wi-Fi, cellular, Zigbee, LoRa, Bluetooth, likewise. So you have to decide. So there are few things for you to know. So Wi-Fi is expensive and has interference. And it's also short range in a secure area. But it has a good you can transfer a lot of data. That's one thing. And cellular, there's a wide area, but still it's expensive. Zigbee, LoRa consumes less power, but it is prone for more failures and data losses. But it can withstand an outside environment. So the things that you have to think about is range, again, important, power consumption, the data rate, and the reliability, how reliable this is. So each and every one of the reason I'm not talking much about this because I am sure that you will have already decided you are going to use this, you are going to use it because device selection and connectivity selection is one thing that's one of the first things that you all do when you are designing an IoT product. But my objective in this session is to tell you that is not the first thing you all should do. You all should do the previous steps and then come to this and doing this. So moving on from that, cloud processing or edge processing. So this is a place that most of you all make mistakes. That is, not everything, every data has to be analyzed in the cloud. Some can be analyzed and processed in the edge node itself. And that doesn't mean you're going out of the IoT framework. It's still IoT. That's why there is a trade-off between edge and cloud processing. If your product, if your solution needs actions fast, if say you read some data, you need to process it and you need to act on it fast. It has to be, the whole process should be sped up. Then you should use a edge processing unit because that has the questions that has the question for minimum time of failure. And also it doesn't depend on things like internet or connectivity. Because if you are trying to process it in a cloud platform, that means you have to make sure that the data is properly sent and received by the cloud platform. And also it takes time given our internet connection. After all, it's Sri Lanka. So all that parameters are going to work on that cloud platform and also getting back to the data. Still, all these latency issues will be there. So make sure that you are using like your decision when it comes to edge processing and cloud processing. Make sure you are taking the right decision based on these parameters. If you want fast decisions without depending on the internet, even though it is Internet of Things, but that's what I wanted to explain. IoT is Internet of Things doesn't mean you have to use internet for every single thing. That is important. It's vital. You can have a cloud software for future depictions and further predictions, like future depictions, or like if you want to further predict or you want to generate reports for all these other miscellaneous functions. But if the main function is time critical, you all should go for edge processing software. So all successful IoT products have a hybrid. So they basically do the edge processing in the unit itself, and they will send they will do the action also in that, and they will do it. And once all that is done, then needed data will be sent to a cloud platform where they will later uh, chart it and visually display that all these actions are done. So that's how it is done. So it is very important when choosing between cloud and edge processing. Now we have come to the fourth step. Can someone answer what are the first three steps? I want to make sure that you guys are actually listening and not sleeping. So can you all tell me what are the first three steps in the chat? Anyone? What are the first three steps of IoT framework? Nobody? Device layer, data connection. Gateway. No. My question is, yes. Problem statement, constraints, and architecture. Yes. So right now we have discussed 3 steps. Developing, identifying the problem correctly, creating a problem statements, and then identifying the constraints, and then designing the architecture. So those are the 3 steps that we have talked about in the IoT frame. Okay. Now we have come to the 4th step, the data life cycle. So data is not important as long as it is properly analyzed and converted into meaningful information, and that information has to be used to achieve a certain function. Even though you convert into meaningful information and still that information is not used to achieve the said function, still your data is not valid. There's no value for data. So once you collect your data, you have to filter it for noise. So different data types, different types of data that you're collecting will have different noise types. Okay, I can't exactly give you the examples. So you will have to come up with software or hardware filters to filter out the noise. And once you have filtered out the noise, and when you have, like I said before, made the data as smallest as possible in the smallest volume, then you can transmit via wired or wireless connection to a certain point. And that data should be stored as well. Some data can be discarded. And those data will be put to analysis. And some of the data will be used to visualization, like drawing pie charts, drawing line charts, bar graphs, all these kind of stuff. Or you can feed it to an AI engine and get a prediction. Somehow in the end, you're going to visualize those data. You're going to, okay, now you will have, in the end, now you come up with your products. You will have beautiful pie charts, beautiful bar graphs. Everything is looking very neat. But in the end, the judge will be like, okay, now what is going to happen? What's the end goal? How we're going to use this data? That is where most IoT products fail. Reading some data and plotting it in a bar graph is not an IoT product. Okay, fine, you did plot in a bar graph. So that information, how are you going to use to solve the problem? So please make sure when you are one day, when you will be presenting your product, when you will be showcasing or demonstrating your product, that visualization, you should be able to justify very well that this exact bar graph, this exact element is directly affecting this component of the problem statement that they initially gave, so that the client is happy. And action doesn't mean always predictive or like a software based action. Let's say something went over the temperature. It was alerted by this device, and it was processed as a critical failure, and the power was switched off. So that is an immediate thing that is done, which is a physical action. So the action can be autonomous, physical, or just a visualization based action. So make sure after all this data and after all collecting the data and analyzing everything, make sure you have very good justification for like that. Make sure you will be doing the actual action from that data. And also, I'm gonna explain to you about some do's and don'ts, which I explained briefly earlier also. Don't send data all the time, by second, minute by minute. No, that is not a successful IoT product. because you have to design the end device or the solution in a way that it will send the data based on certain thresholds or certain events. That is very important. I feel like any IoT product, you can somehow get creative and make a threshold or an event to give a data, because sending data continuously is not an intelligent design technique. It wastes the power, it wastes all the resources, and the edge device is prone to failure very soon. But if you create a event-based method, or if you have certain thresholds, and if that threshold overcomes sender data, that is a very good design technique. So keep in mind, when you are designing your edge node, please make sure that you built a threshold or event-driven method to send your data. And also, once the data is sent, should be aggregated. It should be properly plotted, like properly stored, properly listed down, so that it will be very easier to put to analysis. You have to come up with a structured list, some sort of a structured list. There are so many structured lists in the world. Come with a proper structured list to properly use it, for example, like a queue or heap or something. Because all the data is not important to make the decision all the time. You only need a certain set of data. So you have to make sure your data keeps on rotating and the older data is discarded, the new data is added. Depends on your solution. So you have to come up with that plan, because these are the things that is there in a successful IoT product, not just the MCU and the Wi-Fi. I'm not trying, I'm always saying it not to, not in an offensive way. I'm just saying because even when I was an undergraduate, that's what we always went for. IoT is a ESP32 and some Wi-Fi. That's the main thing that we are talking about. But there are much more than that when developing IoT product. And this is a very important thing, intelligence level. So with all this takeover of this AI and machine learning, not every product needs a machine learning model. I really don't understand why everyone try to have machine learning in a product. So because machine learning was developed into this stage in the recent years, like recent past years. So that doesn't mean before machine learning, there were some sort of IoT products working that didn't use machine learning. Because AI is not mandatory. AI is good. I will never argue with you, but it is not mandatory to have AI in every solution. Again, rule number one, main principle of an engineer: try to make your product simpler, not complicated. Because one thing that you all do is you start off with an IoT product, and in the end, when you're presenting, it becomes a full machine AI powered product. AI powered product, this combination is IoT, not making it an AI powered product. So if you all need AI, absolutely need AI, like, I mean, it depends. You'll have to think more, because right now what we do is, since AI is so developed, we don't think much whether we can use other simple techniques or simple rule based statics. You can just sometimes you actually use if else and get the product running. No, but we would like, because we think if AI is there, that product is a good product. No, that's not how it works. A good product is a product that all of these things are working without failure, and you get the function done. That is a good product, not AI powered product. So please, guys, so make sure that your product actually needs artificial intelligence. And based on that, so there are statistical analysis. You all can research more, see how statistical analysis is done without AI. And there is so many rule engines in Things board and 5 ways you can use it to create more uh, advanced graphing and formulas. And there is no AI in that. So do your research. And if AI is actually needed, use a machine learning model. Okay. Now, first, we developed the problem. Excuse me. We developed the problem, we understood the constraints, and we developed the architecture. And now we developed a way how our data will be, the data will be moving. We know how our data will be, exactly what's going to happen to our data. We developed that. Finally, the security. Why do we need security? I mean, we never think about that part. Why do we need security in IoT product? I want someone to answer this. Like, why do we need to think about the security level in IoT product? Anybody? Why do we need to build in security? Okay, good. Privacy. Any other answers? For data protection? Good. Yes. Okay, we are getting more answers. Protect data. Hackers might mislead the collecting data to avoid misuse and improper management of data. Good. Good. So we are getting good answers. Avoiding data loss. Yes. Okay, we got some good answers. Yes. There has to be privacy. We have to make sure nobody else can tamper it. We have to make sure from the place it was transmitted, the same data should be received at the very end. So when I explain these parameters, I mean, even when you're back in the school, we mainly learn about data protection under three main categories: CIA, confidentiality, integrity, and availability. That means your data has to be confidential. That means no third party should be able to read that data. That means definitely, and also it has to be, the integrity should be there. That means if I send plus 12 from my transmitter, I shouldn't get minus 12 or 12.1. It should be exactly the data that I sent. And also availability. The data should be sent all the time. Like whenever the main coordinator, the main process requests data, it's the data comes to confidentiality. There are a number of things that you can do. Try it out, definitely. Because if you all have actual security built in to your product, your product will definitely stand out. Try out a simple encryption, simple SHA key, some cipher, simple thing. The moment you read the data, feed it into a cipher or a SHA key, encrypt it, send it. So when the receiving end will get some gibberish, decrypt it and get the data. See, simple as that. But then someone will be asking, so what if I directly plug it? If you research on payment devices in the market, payment devices normally, a good payment device has a layer of a layer beneath the screw. Remove the device, there's a layer of there's a copper layer, you call it copper sheet. So the moment someone tries to open it without disabling that sheet, it will short and erase the confidential data. So that is known as tamper protection. There are a number of methods to build in tamper protection to an end device. Research it. Have that in your product. Don't go for complex things. Do a simple thing. Because definitely you will be able to stand out in your stand out as a product. And also one thing is firmware updates. edge devices should always have firmware updates if it is using firmware. Some products, like I said, you can get off-the-shelf IO components that sort of intelligent device. You can have firmware updates. So you can change the keys. You can have firmware updates. You can change the ports. You can change passwords. You can change anything. That's how you increase the security. So these are things that is never thought in IoT design, but it is, which is very valuable. Because if you built in at least one of these elements into your product will definitely stand out, because that is something which is not common, and this is actual industrial practice. So moving on from that, we are nearing to the conclusion of the presentation. So finally, I would when you talk about your overall product, so now you have had did the design, you understood the problem, you understood the constraints, you did the design, you properly analyze your data, okay, and you build the software, and you thought about the security. Okay, now everything is complete. You deploy it. The real problem starts happening once you deploy it, because your product should be able to handle faults, and also it should be reliable. Like I said, always expect any layer of that architecture to fail. Common failures are connectivity issues, network outages, power losses, sensor failures. So these are common issues. So what will be the solution for these failures? Because say your sensors try to fail, what will be your solution? So the easiest solution is because you are anyways reading things periodically, you can send data packet. If it's not responding, if the data is invalid, you can send an alert to a human operator to go and check this set device. So you have to have these fail safes. I'm not saying the moment sensor one fail, you should have another 4 sensors to go to sensor 2, 3, 4. No, maybe okay, sensor fail. Okay, the device is not working, but alert goes to a human operator automatically or somehow, and that it will be directed there, and they will replace the sensor. Devices fail, goddamn rockets fail. So definitely this your edge device is going to fail. And power losses, definitely. Sri Lanka, power is going to, if you're connected to the mains, please expect that power is going to go at least 2-3 times a month. So once the power fails, what's going to happen? Does it switch to battery power? Is there any contingency? So these are things about network outages. Your connection is not going to be the same, because wired or wireless, even wired connections are not reliable too, because due to various other physical parameters, wired connections can get broken down, and also wireless connections. So make sure if your data is very critical, because some data is not critical. Say at 8:15 p.m. we are sending data, but it didn't go, the connection failed. But if you send the data again at 9:15 p.m., they can calculate it and backtrack it. So that's not very critical. But if the 8:15 data is PM data is very critical, and if the power is fail, have an EPROM, have some sort locally, at least for an hour. Maybe I'm not saying forever, but say at least it will try to regain the power for an hour, and the EPROM will be, if the EPROM starts to go over capacity, then you can send a notification, or you can keep sending notification. You can put change the state of the device to send notification saying the EPROM has failed, the connections are set, because the moment the power restores, it will send the data. So these are these small design things that you can get creative. You can have different contingencies. Don't overcomplicate it, but have small design contingencies for failures. Because if your product is actually fail safe, that is willing. If your product is secure, that will stand out. Just because you send some data, it goes to the cloud, it processes it, and the machine learning model gives a very nice prediction, doesn't mean your product is a success. Your product should have all this. Should be reliable, fault handling, security, everything. So now let's move on to a case study. So this is a real life case study. I developed it using actual project that we did recently in our company. This company is a garment. They are manufacturing garments. There's someone is raising their hand. If you all have questions, you can drop into the QA box. So now there are 105 attendees. There's around 95 attendees. So I want you all to work with me on this. I want you all to drop in the chat QA box for this case study. I'll give you around 2 to 3 minutes. No need to go to full details. Just to practice it. So the case study is as follows. There is an assembly line. It is a U-shaped assembly line. The meaning of a U-shaped assembly line means you start from one point, they do something there, and they send that piece of product to the other line. So they add something there and they send to the other. So that's how it's done. So you start from 1, the raw materials are given from 1, and when it comes all down to 10, you get the finalized product. So that is the structure of the assembly line. And there are workers working in each section. So for example, you start from heat printing and you go to trimming and you go to sewing and you go to molding. Likewise, you labeling and packing. Likewise, you go. And also there can be 1 or more machines for each station. Say now there can be 2 molding machines. There can be 3 sewing machines. Likewise. So that is the structure. The problem they have is employees. The incentives for employees are calculated based on the number of units they actually work on. They manufacture. So if I'm working in the trimming machine, if I complete 50 units of clothes, if I neatly trimmed 50 units of clothes, I will get an incentive based on that. So that is the incentive. So existing, what they did in the previous time is a human operator would come every time when their shift is ending. So there are 2 shifts per day from 8 to 12. Sorry. Excuse me. There are 2 shifts, one from 8 to 12 and the other one is from 2 to 6. So nearing the end of the shift, a human supervisor will come and note down the amount of products from each and every line. But the thing is, it's human. They are prone to make mistakes, and also they do favoritism. So say if I know you, I'll be like, okay, since we are close enough, I put additional units for you. So you get more. If I don't like you, I cut down your incentive. So that is a problem. And also, that's problem number 1. Incentive. There is no proper way to calculate the incentive. Second problem is, so say you input 50 units, you have to get 50 units in 1 hour. But you don't get 50 units in 1 hour, you get around 25 units. That means in one of those stations, there is a bottleneck, there's a delay. But they are not able to properly identify that the bottleneck is in that exact location, that there is a delay. Because without identifying the proper place, they can't add more machines and workers to prevent the bottleneck. So that is the second problem they have. Normally what they do is they assume the bottleneck is there and they add machines. The third thing is they don't have a proper system where all these data, all these production patterns or everything is properly logged in, where they can make predictive analysis in the future to create production plans. That is, those are the problems they have. Now, now I want you all to go through number 1, 2, 3, 4 steps. Security, of course, you can do. Security also, just think of now, properly give me a problem definition. So I'm the client, properly give me, because even though I said the problem, you define the problem back to me so that we are on the same level. Properly give me a problem definition. Give me, understand the constraints. So this is a factory. These are clothes. This is the environment. And also, one thing is, these machines are not permanent. That means, say, today it's trimming, sewing, and molding. The next production plan, they will remove the sewing machine and they'll add another trimming machine and another different heat printing machine. So the U shape is not permanent. It is dynamic from production plan from the product to product. From different clothes to clothes, they change the U configuration. So those are the constraints. So quickly, I'll give you a few minutes. 8:22 until 8:25. I want you all to drop in the question box the constraints that I will have, the problem statement, the constraints, and a design. What would I do roughly, so that I know that you all actually have understood? Anyone who would like few answers quickly? So these are the steps. Anybody? Doesn't need to be very detailed or anything. I know within this time frame it's hard to do it. Just whatever you all feel like. There are no wrong answers. Just whatever you feel like. You can put 1, 2, 3, and likewise, so that I know it's a step. Just to know that you have come some sort of idea. I'll give you another 2 until 8:28, and I will continue the presentation. But still, you all can add your answers. Okay. So this is the design that we did. So the problem statement is that they are unable to calculate the incentives due to favoritism and things like that. And also every time there's bottleneck, they can't identify it, and they assume it, and they need a way to properly visualize all this data for the higher management to make predictive decisions in future production plans. So every machine has a moving part. So what we did is we tapped in to that moving part to sense the machine on time and the machine off time, because the human time, the time it takes to load a material to the machine is the time the machine is actually off. Then the machine time is constant since most of the machines are automated. Like you need a human to press the button and do things like that. So machine time is constant. So we tapped in to that movement and we got a pulse. So, and every time it goes up and down, the pulse, I mean, not the machine, because we tapped into a relay of the machine. All machines have PLC. We tapped into a relay and we fixed a off-the-shelf IO device. So this IO device consists of a digital built counters. So every time it goes up and down, that it increases the counter by 1. And we send this, since the floor plan is always dynamic, not permanent machines, we cannot go with a wired solution. Since Wi-Fi is, there are so many Wi-Fi interference inside the building itself, because there are so many networks, there are organization networks running inside the building. So we can't have another separate IoT Wi-Fi working for this, and it costs a lot. So we went with a much more low cost device, which is we have low cost connectivity as Zigbee. So every unit consists, every machine is connected on the surface, as you see in the image, is connected with that box. So that box contains an IO device and is powered by the machine power itself. So if the machine fails, if the machine power fails, so this thing also fails. So, but I'll tell you how we know the machine is down. So we send that data through Zigbee. So the connection between Zigbee and the IO device is RS-485, which is the industrial protocol. The Zigbee sends the data, and the coordinator receives all the packets from the specific routers. So we actually fix routers on each U-shaped, on top of each U-shape, so that there won't be interference, and there will be connection. There will be complete connection to the coordinator, and the coordinator is connected to a single PC, and the PC is connected to Wi-Fi, and the PC is running a Python source script, a desktop software, which collects this data and which is pushed to the ThingsBoard server. In ThingsBoard, there is so much analysis that is being done. So in ThingsBoard, since we are sending the counter value with the timestamp, it puts this timestamp and the counter value to a formula, and which it will give the machine on time and machine off time, the operation time. And also there's a threshold. So if it goes beyond a certain off period, we determine it as the machine is down or the machine is under maintenance. And in ThingsBoard, we have created a large number of dashboards separately for different things. One dashboard is always shown in the factory itself, so that people know people or in lively, while it's working in live, they can see their products, the number of units that they have manufactured, and at the same time, higher management can log in and check other predictive analysis, because there is always a chart. So we plot a live chart with they can see the chart is going down or up, whether the production is meeting its demand and things like that. So this is I'm saying high level. There are much more things working together, but this is the solution that we came up with. But this solution is not very effective, because, like I said, all the analysis is done in the ThingsBoard server itself, because we only get a counter value and a timestamp. So we realized that it is not very effective. Then we redesigned the edge node with a PLC. So the PLC tracks the machine on time and off time, because at the moment the machine is on, it has a timer running, and the moment the machine is off, it stops the timer. So it sends separately the machine on time and the operation time, not a counter value. With the counter value, with the timestamp, it also send two other time values for human operation and machine time. So that which is more accurate than this IO module. So like first that's how you do. I'm saying it in a very, very high level. There were so many rounds of design for this product, but that is the main part. So this is the real world. So now it's successfully running as of now with PLC. Settle down. So let's quickly move on to common IoT mistakes that you will do. First of all, solving the wrong problem. Always. We start off from somewhere, we make some other device, and later only realize we didn't solve the actual problem, we solved a different problem. And over engineering, I always say, number one principle. Keep your design simple. Make your design simpler. The job of an engineer is to not make a fancy product. The job of an engineer is to make a reliable working product, functional product. Ignoring it, like I said, without maintenance, the IoT product will not suffice. Like it will not maintain. So you should have a proper way to easily maintain the product. Say now you have a device, say it's using battery power. You should design the enclosure in a way that you can easily remove the battery and plug one in if the battery fails. No need to remove the whole. So that is a design constraint that you have to think about when thinking about maintenance. And definitely poor security. And also, like I said, if the requirement increases, your device should be easily able to scale up or down. So the lessons learned from industrial practices and all these years of my limited experience, that is smart, small, and then scale. First, try to make a minimum viable product and then add features one by one. That is what you do. Because you can design everything. You have to design security, you have to design each and one of these things to the product, but you start adding them one by one. You don't write everything and deploy the product, because if it fails, you don't know from where it's failing. That's how, because that is known as feature development. That is actually practice in software. You develop features one by one. You develop the hardware one by, like in the previous example I said, we first choose IoT products, IO module, simple one, but it didn't work. Then we develop the feature using a PLC. Gradually. Field testing is critical. If whatever the IoT product you make, you have to have tests. You have to definitely run your test in that environment itself. If your end device is going to be in a forest, just because you run it in the lab doesn't mean it's going to work in the forest. It has to be tested in a forest. If it's underwater, it has to be tested underwater. Wherever the wherever the place environment you plan on deploying, you have to make sure your device are tested in that environment itself. And hardware issues appear later. At first, the hardware will run perfectly. So many issues happen even when we're deploying this previous example I said. Suddenly there can be later losses. Suddenly the power starts, suddenly the IO modules starts getting burnt out because there's a power failure. And sometimes the data are corrupted. Sometimes we start missing data. So hardware issues starts coming later. So that's why you develop it one by one. And then again maintenance. So as to conclude my session for today, the key takeaways I would like to say, IoT is about decisions and actions. So that is what a successful IoT product is. Not gathering data. That is just an electronic device. Gathering data is not an IoT product. Machine learning model is not the IoT product. Creating the decisions and then acting upon it is the IoT product. That is a product you give. You make this decision and you do the action. Like a blend. Has hardware, software, everything neatly integrated. So that integration has to be done well. It has to be tested. And guys, I'm telling you by experience, when you're testing, don't test it in the happy path. Try to somehow fail the test. Because if you somehow try to fail your test while testing, then only you'll be able to successfully develop a device which won't fail in the actual scenario. Anything. So you have to make sure that your device, when while testing, is tested for failure, both hardware and software. And like I always say, which is the whole objective of presentation is problem definition. Once this session is over, from tomorrow onwards, pull up your proposals, think about the problem again, and see whether you have thought about every single thing in this problem, whether you have properly collected the problem definition. Grabbing something out from the air and taking it and creating a product is not a, that's not how you define problem. You should take an actual problem and make sure that IoT can give a solution to that problem. You don't create an IoT problem. That's the thing. That's what you should do. Sometimes your problem might not even need IoT. So make sure that your problem is properly defined, and it is to that problem you can give a successful IoT product. And finally, simplicity. Again, the engineering principle number one, make a simpler product. And like always in my all the sessions, I say learning, because you're all undergraduates, learning doesn't stop after your university life. Learning actually starts after your university life, because as an engineer, you have to keep updating and learning, because the world is changing in a very, very fast rate. Things are changing very, so you have to keep on updating yourself. So the actual learning starts once you are graduated. Thank you. So let's move on for questions and the answer session. The requirement of efficient automation warehouse repairing techniques. Many devices are connected to the same network and all of them reach the threshold at the same time. How can we prevent the network from collapsing due to one? Devices are connected to the same network, okay, and all of them reach the threshold at the same time. How can we prevent the network from collapsing due to high traffic? Okay, then again, that's a good question. So then again, what I have to ask is, how critical is your data? Because depending on how critical the question was, if many devices are connected to the same network and all of them reach the threshold at the same time, how can we prevent the network from collapsing due to high traffic? That's the first question. So depending on the criticality of your data, it differs. If the data is not critical, you can always have, you don't need to always send every time the threshold is set. You can record this data and send it periodically, because you can make sure you call all these devices periodically. You can do that. I don't know whether it answered your question, but that means say your device, everything uh, it reaches a certain threshold, you note it down locally, and after some period, your main coordinator will do a full cycle of readings. Then you will get, then that the whole network won't be congested because everything one is sending data. You can do that depending on how critical your data is. That's there. And if your data is actually really critical, you will have to have more networks. That means you should have sub coordinators, and sub coordinators should talk to a main coordinator. That means then you know you are exactly having a sub coordinator to the amount of devices that can send data at the exact same time without failure, because you have to test it. Say 5 devices can send data at the same time to the network without failing, so then you can have only 5. So then you will have to have multiple if your data is critical. Say. I'm getting a lot of questions. I'm trying to understand which one I answered. Where does the majority of the data processing happen, at the edge or the server? Again, it depends on what product, what depend on you are doing, what data you are processing. It depends on the final action. If your action is very fast, then definitely you have to process it at the edge and send the output there itself. But but with that, if you want some future other predictions which is not very time efficient, then you can send that data to your server and later uh, analyze it and send it back to you. It depends, guys. All most of these questions depends on the data, the criticality of the data you are using. How do you determine which data is smart enough to be sent immediately versus what can be bashed or discarded? How do you determine which data is smart enough to be sent immediately versus I actually don't understand the question. So, maybe you're asking is how do you determine whether the questions are whether the data is critical enough, I think, or data is smart enough to be sent. So again, you know what your product say. So I am the farmer. My crops are dying. So you exactly know what the data I need to make sure my crops are not dying. So you know exactly what data to be sent fast and what data you can send. It depends on the product. I don't know whether that's the best answer you were looking for. When should you care environmental factors like recommending? So environmental factors is so in electromagnetic interference. It be so say you are doing an IoT project. You are actually deploying uh, devices in a factory environment, like with so many motors, like three-phase motors or like three-phase motors, high-end, high powerful motors, AC motors. So AC motors generate a lot of electromagnetic interference. So you have to place your device and start test it there to see the amount of electromagnetic interference, whether it is actually affecting it. And there are some, say your device is actually interfered by that or your connection, then you will have to design a PCB. In that case, you will have to design a PCB. You can't buy an offshore. You will have to design a PCB with limiting electromagnetic interference. So there are a number of ways, if you research, how to design a PCB to limit EMI interference. So you have to test it and see. One thing I have to say is, guys, I know there is a framework, but that doesn't mean if your product is going to be successful at once. There is a nature when of every product when it comes to hardware and software. You have to go many cycles to make your product successful. That's how everyone is done in the world. You can't get it right the first thing itself. So don't worry about it. But stick to the plan always. Can I make this project, my project, some part with an AI identification system or internet? Mahan, I'm not sure what you have answered or what you have asked actually. Can I make this project? Yeah, yeah. Guys, one thing is I am not aware of the project requirements for this comparison. I'm not aware of it. So if you're asking me a question regarding when you ask me whether you can do something, if there are limitations of they've given rules and regulations of what your product can have and cannot have, please refer to the organizing committee and to the relevant people. Anything from this session, if you all want to know, please ask. Not the how what your product can have for the comparison. I am not aware of it. How does the host machine work? So, how does the host machine verify that telemetry data is received actually comes from HTML capturing device? Encryption and decryption. Because you are the one only know how you decrypted and encrypted and what's the key is. So if you decrypt it, and if it is not decrypted properly, you will know that this is coming from a legitimate edge device. That is one thing. Or you can have one thing. The other thing is you can have a generated pre prefix prefix and a suffix or some other characters that which is unique to you. You can design a prefix and a suffix. So every data packet you add a prefix and a suffix, whether it's a random number and a number and a special character or something. So then when it receives, you have to check whether the data is starting from say one at symbol, something like that. So then you know this is coming from legitimate this thing. What is the best practically way to send an image through a GSM model? Best practical way to send an image to a GSM model. Hmm. What do you mean by best practical way? You have to convert the image. What is this software algorithm? I will get back to you regarding that. I can't remember the name for that algorithm. You can break it down very easily. Is it worth to create a custom optimized protocol for spending specialized data? Yes. I mean, then again, you have to make sure your thing. I mean, you can come up with your own protocol for specialized data. It is good, and it's not easy because once in the project we try to come up with our own customized a Modbus 5 Modbus protocol, and it did not work. So we had to go back to the normal industry protocol. So make sure if you're using your own customized protocol that it is working perfectly, because if the protocol fails, everything fails. Using SIM900 model for communication, will it be IoT device? Yeah, yeah. Guys, IoT doesn't mean always wireless, always using internet. It is not IoT. The concept of IoT is those layers. So there's always a edge device. It communicates to something, it processes and visualization. So definitely you can use SIP900 model for IoT. Mm. Uh, if cost is high and it is a fast method, there's also have a the cost is high and it's a fast method. There's also have a cost is low, but it's also slow. So you are saying the cost is high and you have a fast method, but the cost is low, but you have a low. So first of all, you have to think what method do you want. Do you need your data to be fast or whether your data to be slow? If you can design your way, if that data is not very critical and if you can have some latency, if it needs to be slow, yes, you can go with a low cost one. But then again, when you use a low cost one, will that sensor work in that environment you're going to deploy? Will that sensor draw minimum power? Will that sensor withstand that environment? So there's that thing you should also think, not just the speed. So those few things you have to answer to me for exactly to tell me whether it is better to go with that or not. Anything else? Any other questions? So the person who asked the best practical way, can you clarify to me whether you're using GSM? When you say GSM, you're using whether you're using SMS or GPRS, like you're whether you're using internet or just SMS. Because back then, from an SMS, we had that those Nokia phones had that what do you call MMS, right? Multimedia messaging service. Yeah. So we send small pictures through MMS, but those were actually small, like vector sort of a thing, which is black and white. So if you can break down your image to that, I think then you'll be able to use the MMS service, but I don't know whether it's active now. Gaia, can you clarify to me whether you're using SMS service? Yeah. So that's the problem. Uh, I'm not sure whether the MMS services are still working through the current data corrections that we have, like Nokia and Dialog. If it's working, still there is a type of image that you can send. You have to do some research regarding that. I think that's the only way that comes to my mind right now of sending an image to a GSM model. You can't send a full JPG through SMS. That is not possible. Unless you run a separate software in the edge node to break the full image to like into hex values or something. And then you will have to send it through SMS. I don't know whether this actually the way you're asking is practical. Any multimedia content can be broken down into hex values. No? You can send that, and then the receiving end has to reconstruct the values one by one. And if one single byte fails, you can reconstruct the image. So that's the problem. It's not practical. And you'll have to go with a different connection, or you can check the MMS thing also. I don't know whether you've checked it, but see if still they use that service, and if the service is still there, what type of images you can send through. Okay, I guess the questions are done for the day. Hmm. Madhumi, I would like to
Okay, sir.
hand over back to you.
Thank you very much, Mr. Dewmith, for patiently answering all the questions and for sharing such valuable insights with us today. We truly appreciate the clarity and practical perspective you brought to the session, especially at such an important stage of the SLIoT Challenge 2026. Thank you so much.
Yes, you're welcome, and I wish best of luck for all the participants in the competition.
Thank you, sir.
Thank you. Bye.
As we near the end of this program, I would like to invite the Vice Chairperson of the SLIoT Challenge, Mr. Yazuru Bandara, to deliver the vote of thanks.
Thank you, Mathmai. So I would like to sincerely thank Zone 24 for their incredible support and for joining SLIoT Challenge 2026 as one of our knowledge partner. So to empowering our participant with industry-level IoT guidance. So special thank you to our guest speaker, Mr. Dewmith Ranasinghe, and our academic advisor, Dr. Kutila, and the SLIoT organizing committee, and the SLIoT delegates, and everyone else who supported and contributed to making this session a success. So following today's session, actually, you will have 2 more upcoming sessions On the 25th of next week, we will conduct a session on how to empower your IoT device with AI and machine learning. And also we have a session in the following week. You will have how to market your product, how to build the business model for your product while the proposal submission stage. So we strongly encourage you to make full use of these opportunities and finalize your project proposals before the deadlines. And so a large number of teams have already registered, and this is your chance to fine-tune your ideas and rise as future leaders in the IoT industry. So as we mentioned earlier, this is not just another competition. So this is a platform that we can shape your IoT future. So the SLIoT Challenge 2026, organized by the Department of Computer Science and Engineering, University of Moratuwa, in collaboration with SLT Mobitel and IESL, is designed to truly empower and elevate you. So thank you once again to everyone, and have a great night.
Thank you, Yasuru. This concludes the first session of our Zone 24/7 technical series. We warmly invite you to join us again for the second session on 25th January, where we will further cover technical aspects essential for the proposal submission stage. We encourage you to make the best use of what you have learned today and apply it confidently in your SLIoT journey. With that, we come to the end of today's session. Thank you all for joining us. Have a great evening, and we wish you all the very best in the journey. Signing off, I am Madhumai Swendhan.